Now we'll briefly cover consistent and inconsistent systems of linear equations. Very simply, a system of linear equations is consistent if it has a solution, okay, at least one solution. And it's inconsistent if it doesn't have a solution. So if you think about your experience so far with solving systems and writing them as the coefficient matrices, when you think back, what are the possibilities for it to not have a solution? We only really saw one. Okay, so we might have a system that looks like this. With the coefficients here, we might have what's called a leading one here, maybe a 0 and a 3. Okay, so if we were to interpret this as a linear equation, it would be x is equal to 3. So far, so good. But then I believe we saw something that looked like this. Okay. Now, if we interpreted this as a linear equation, we'd have 0x plus 0y equals 2. So this second line here, this means that 2 equals 0, which is not great. We don't want that to happen. So if it does, that resulting system is inconsistent. It doesn't have a solution. Okay? So if we don't have that situation, we have a consistent system, and we can think about how the solutions might work there. So one case, and I'll draw a 3-row, so 3 equation in 3 variables system. What I'm going to do, I'm going to introduce this convention of drawing a vertical bar here to separate those coefficients from the constants on the right hand side. And these could be anything. Let's just put something down at random. Okay. So in this case, if we interpreted this as linear equations, I'd have x equals 3, y equals -1, and z equals 5. Great. It's consistent. That's the solution. Right? We might write a solution as x, y, z equals 3 minus 1, 5. Great. That's not the only possibility. We might also have something like this. Perhaps we have, again, 3 variables. Seems like I always pick the number 3 for my first row. We may have 3 variables, but only 2 equations. And I'll write it like this. There. Okay, so this corresponds to 1x equals 3, 1y equals 2, and z's not stipulated. It's not like here where we have z is equal to 5. There's no row here that gives a condition on z. So z ends up being what's called a free variable. Normally we write it something like this, like z is some variable. Different authors will do it differently, and we might say that that variable t is in the real numbers, just to indicate it can be any real number. Okay, so this is a consistent system. It has a solution. Just so happens to have infinitely many solutions. Okay, and that's what this box here is indicating. Okay, let's look here. If a consistent system has a free variable, it has infinitely many solutions. So that's this case here. Got a free variable, has infinitely many solutions. This first one, a consistent system will have exactly one solution if and only if we have leading ones for each variable in the system. So there's 3 variables. There's 3 ones, they appear along this diagonal like this. Okay? Great. And we'll do problems that look at these types. And I'll just project some right now. Oh, sorry. I've got one more slide before we do that. If you think about how you might have an infinite number of solutions, you can probably come up with a few possibilities. First, if we only had one solution, you think about it, it would be like I wrote on the previous slide where I have x, y, z is equal to 3, minus 1, 5. Well, that's a point in three-dimensional space. So that's what it looks like when you have exactly one solution. But if you have more than one solution, that can look like different things. For example, in two-dimensional space, I could have my 2 linear equations, represented by these 2 lines, overlapping. Okay? So then all solutions are points on these lines, which are the same line. Okay? So there's infinitely many solutions, and the geometry of them is that they form a line. Okay? But when we move to three-dimensional space, you could have equations that represent planes. So the planes can intersect in different ways. They could intersect along a line, like this, 2 of them. Okay? Or they could all intersect together, just like in the two-dimensional case, they could overlap. Well, in this case, they're the entire plane, an entire plane of solutions. Okay? Let's take a look at this here. Let's write it first as a coefficient matrix. And what I'll do, I'll write it in this, some authors call it an augmented matrix. And what they have here on the left are all the coefficients from the x's. And on the right we have our constants. Okay. And you can see if I add 2 times row 1 to row 2, I'm not changing row 1, but my row 2 suddenly becomes all zeros. Now if I were to reinterpret this in terms of systems of equations, I would have x1 plus x2 is equal to 1. Okay. This is an equation of a line, right? x1 might be like your x, and x2 might be like your y. So I could rewrite it like this. Okay. If I vary x, if I change the values of x1, I should say, then x2 changes in response. So there's only one variable here. Let that variable range through all real numbers. It sweeps out an entire line. Okay. Here's some equations. Systems of linear equations. Each of them have 3 variables. Okay, and there's 3 equations in each. Your task is to find if they are consistent or if they're inconsistent. And if they are consistent, come up with the solution and tell me what it is. What would it look like if you were to graph it? Okay? And this is something we can talk about in person.